This Tuesday evening. And first of all, we need to apologize for not being here last week, which was entirely my fault. Well, not my fault, but we had Storm Harry hit Spain rather badly. We had 24 hours of non-stop intense rain, and then we had a power cut that lasted 18 hours. So I'm afraid that as my machine hosts the live stream, we weren't able to bring you Space Oddities last week. But
we didn't feel like it, so.
Yeah, but there is that. Well, obviously that as well. Didn't feel like it. Couldn't be bothered. But anyway, so apologies for that. But everything that we were going to do last week, we're going to do this week. So you haven't missed anything. So thank you for your forbearance. So on a packed program tonight, as part of our commemorations, to commemorate 20 years since the launch of New Horizons to Pluto. The anniversary was on January the 19th last week. This evening, we're going to be looking at some of the science that's come out of New Horizons flyby of Pluto and what we found out about Pluto. Also, in regard to Pluto, don't forget that next week we are going to have Dr. Alan Stern joining us. And Alan Stern is the man who basically put the New Horizons mission together and fought for it to be launched in the face of much skepticism from NASA and other people. So Alan will be joining us next Tuesday, same time, on Space Oddities. And we hope that you will join us and ask Alan your questions about Pluto, because it's his baby, really. So that's next week on Space Oddities. I'm joined this evening by a bunch of unruly crew. That is to say, Daz and Roger and Michael and Dave. And hope you're all okay, gentlemen. I'm raring to go again.
Lovely, thank you.
So
lovely, thank you.
Yeah. So what have we got apart from Pluto tonight for you? Well, as you're doubtless aware, there was an amazing solar storm last week, and Daz is going to be telling us all about that. We've got the usual features. Dave's got quite an enlarged the week of tonight, which is great. We will be having the Einstein of the week, which has got an absolute gem this week. Stick around for Einstein of the week. And Constellation of the week as well. Roger's Night Sky Gallery, usual stuff. So to get started, first of all, if you're new to Space Oddities, thank you for joining us. We hope that you'll stick around. And if you've been here before, thank you for coming back. That's all I want to say. So don't forget, if you would like to support Space Oddities, you can, of course, firstly, buy us a coffee. And all of your contributions towards our caffeine levels go towards keeping the channel running. You can scan the QR code that's on the screen, or you can click the link that should have just appeared in the chat. Don't forget, we've got our Space Oddities t-shirts. So if you would like to get yourself ready for the summer by buying an absolutely glorious Space Oddities t-shirt, you can do so again by scanning the QR code or clicking the link that's in the chat. And as it's winter, you may prefer to get yourself a Space Oddities hoodie. And again, reasonably priced, very good quality. Price includes UK postage and packing. If you're outside the UK ordering any of our merchandise, please add £10 to the total value of your order. And there we are. You can also make a donation directly to Space Oddities by clicking the super chat icon. That's the one with the $sign directly under the chat window. And why not join our Patreon, where just for a few pounds every month you can support the channel, keep us going, delivering you the type of astronomy and space related content we love to give you. And you get all sorts of goodies there as well. And I will just put that up on the screen. If you want to join our Patreon, it's very, very simple. Simply go to patreon.com/Space Oddities and join the community there. And thank you all so much for your continued support. We couldn't do it without you. So thank you very much for all of that. So what else have we got? Well, we've got a number of different things coming up over the next few weeks that we'll tell you about in good time. And I think we'll get straight on with the show now. And in time honor fashion, we're going to go to the news. One big thing that was in the news last week was this. It was the rollout of NASA's SLS rocket to the launch pad in time for the launch of Artemis 2 on its circumlunar mission with 4 crew members, and that will be launching. I think it's is it the 8th or the 9th, the latest date? I can't remember. Anybody know?
Seems like the 8th is what I remember.
I believe it's still the 8th.
Right.
It's still the 8th UK time, yeah.
Yeah.
I know the astronauts are in quarantine.
Yes.
Right.
Yeah.
That's right. And could somebody just look up the launch time? I know it's early in the morning UK time.
Give me a second.
Thank you. So whatever the time, though, we will be bringing you on Space Oddities live coverage of the Artemis 2 launch. We really hope you can join us for that. Ask your questions, have a chat, and we will hopefully look forward to seeing you, even though it's in the early hours of the morning. But we will cover it nonetheless, because we always like to cover these major space launches live. And good luck.
It's the time, UK time, it's 2:41.
Right.
UT.
Right. So 2:41 in the morning.
Yeah.
On the 8th of.
It's actually on February the 7th, 2:41.
Oh, February the 7th now, is it?
Yeah, that's the actual date. Yeah.
Okay. So
right.
Hope you can join us. We will be going live then about let's say 2:15 on 2:15 in the morning on the 7th of February. If there are any changes to that, as there may well be, you'll see the changes on the live stream on the channel. So we'll post the live stream very soon so that we can keep you up to date on any changes. So there we are. So that's Artemis 2 going back to the moon after so many decades. The crew of 4. They won't be landing on the moon. They will be flying around the moon. And lots of people on social media have been saying, "Oh, can't we even go back to the moon anymore? Why aren't they landing on the moon?" And of course, they're doing it for the same reasons that Apollo 8 did for Apollo 11, a dress rehearsal to test out all of the systems, particularly the life support, of course, ahead of Artemis 3, which is now planned to land humans on the moon in the first part of 2028. And remains to be seen whether they'll make that date, but we will see. Lots to get through before then. Okay, let's now just go over to the rest of the news for this week. I haven't got that many stories for you this week, but I hope that you'll enjoy these. So let's just get to where I need to be. Let's put that up there. And give me 1 second. Okay, so this is the news for the 27th of Jan. And first, we've got 2 stories about cosmology this evening and 2 about the moon. So the first is this. This is an amazing image. Let me tell you why. This is one of the most detailed maps yet of dark matter's influence on the cosmos. This has been produced using data from the James Webb Space Telescope. It's a new high-resolution map covering an area of sky about 2.5 times the apparent size of the moon. And this reveals how invisible dark matter's gravity has shaped the formation and distribution of galaxies and other cosmic structures. Now, by tracking subtle distortions in the light from hundreds of thousands of distant galaxies, using a technique which we've often talked about here on the channel, gravitational lensing, researchers have mapped dark matter with finer detail than earlier efforts, including those based on Hubble data. In this image, you can see here that areas of equal dark matter distribution are shown, with the high concentrations shown in blue. Now, why is this important? It's important because these observations confirm that dark matter, which, as we know, does not emit, absorb, or reflect light, acts as a gravitational scaffolding. Its clumps drew normal matter together in the early universe, guiding where stars and galaxies formed and ultimately influencing the large-scale cosmic web. In addition to doubling the resolution of previous maps, this map produced from Webb data identifies new dark matter concentrations and offers a sharper picture of the correspondence between visible and invisible matter. Now, these results bolster the standard model of cosmology and provide fresh insight into the role of dark matter in cosmic evolution. So, Lou, have you got any comments about this being a sort of a monde man?
Yeah, I would say the presumed dark matter, since we can't find any evidence of physical reality around it. But it does seem that to end up with a universe with the structure and density now, that it does require some sort of dark matter, particle, substance. So I think this is great, even though it doesn't really exist.
Yeah, so
working for you.
Yeah, exactly. Yeah,
this is modified Newtonian dynamics audience, which just says that we don't need particles. We just need to modify the stalwart 400-year-old never failed equations of gravity. But most cosmologists,
it's basically cheating on homework.
Believe there is.
It's cheating on homework.
Yeah.
I think the expression "clutching at straws" comes to mind there, Lou. But never mind.
Ouch.
Oh, don't bring.
I have all of my "I told you" ready to go, so we'll see.
Okay, right. But we will have that debate. We must schedule that. Viewers, we've been talking for ages about having a debate, modified Newtonian dynamics against dark matter. So perhaps we'll do that one week. Okay. You no doubt know what this is. This is a map of the cosmic microwave background. Now, there's some really interesting and potentially revolutionary new research, which suggests that dark matter and neutrinos may interact. This challenges the long-standing assumption that they don't influence one another. It opens a possible path to major advances in cosmology and particle physics. Now, this study has been published in Nature Astronomy, and it draws on a wide range of cosmological observations, including the study of the cosmic microwave background and large-scale structure surveys, to model how a subtle exchange of momentum between dark matter and neutrinos could affect the growth of cosmic structure. This interaction appears to ease a persistent discrepancy known as the clumpiness problem, because the prediction is, by current models, that the universe should be more clumpy. That is, there should be more concentrations of matter, more pronounced clustering of matter than what we actually see today. Now, if you say that dark matter and neutrinos actually interact, the simulations come out more or less exactly as we see the universe today. So this is really interesting stuff. The only problem at the moment is that the significance level statistically is only about 3 sigma, whereas really 5 sigma is normally asked for as an indication that it's a real observation, that it's speaking the truth. But 3 sigma is good enough for further research to go on. And if it is confirmed by upcoming surveys and analysis, it would represent a fundamental breakthrough in cosmology, prompting revisions to the standard LCDM cosmological model. That's the lambda cold dark matter, I'll say that again, lambda cold dark matter model, and giving us fresh insight into the nature of dark matter. So the interaction between dark matter and neutrinos is going to be very tiny, but on large scales, it could have had a big effect on the so-called clumpiness of the universe. So that's promising as a new discovery. So we
add something to that, Andy.
Of course.
There's some recent research, very recent research, and I'm sorry I don't have the reference, that was much higher of type 1a supernova that were testing the lambda cold dark matter model against the W cold matter model, which allows the dark equation of state universe to vary a little bit. So lambda cold dark model doesn't vary. WCDM model, it varies. And it was interesting that these studies, these much more accurate to type 1a supernovas, pretty much supported both models.
Right.
Yeah, so that remains to be something to sort out.
But I think this is a really interesting possibility of neutrinos and dark matter particles, whatever they are, interacting. But we don't know the mechanism, obviously, of exactly how the interactions work. But it's got to 3 sigma, so that there is something going on there by the look of it. So interesting. Thank you for that, Lou.
Yeah, I think is still favored as the standard model,
Yes.
but neither are ruled out.
No, well, this is science after all. This is how we progress. So let's move on now. Let's go closer to home with the moon. And can anybody tell me what the time on the moon is?
The time on the moon.
Yeah.
Is it Miller time? No.
Yeah, because I know they're talking about using the lunar time, aren't they?
Yeah. Why?
Well, it should be GMT, of course.
No.
Is it
Yeah.
noon?
Obviously, you just
invented
extend
time.
the Greenwich. Yeah, you just extend the
It's
Greenwich.
high noon.
Yeah.
The sun is directly overhead.
I suppose if you're right on the meridian there, facing the Earth, yeah.
Yeah. You just extend the Greenwich meridian out into space and it goes to the moon.
Yeah.
Hey! It's U.S. flags on the moon, so I think we get to say.
I think they all got blown over, didn't they?
Well, they're all.
Bloody well time we say it is, right?
If not, they'd be
Well, the
sitting on
problem here is that time on the moon ticks faster than it does on the Earth.
Right.
That's right. General relativity.
Yep.
Exactly. And the difference is tiny. It's about 56 microseconds per day, but this builds up over time. Yeah. So when you are mounting space missions that depend on absolute precision of time, you've got a bit of a problem. For navigation, communication, any precision lunar operations that rely on time could have problems. Now, the clever Chinese have come up with the world's first lunar timekeeping software, and it has the impressive name of LTE 440. Of course it does. And the LTE stands for Lunar Time Ephemeris, and it was created by a team in Nanjing at an observatory that has the wonderful title, a beautiful title of the Purple Mountain Observatory. There you are. It incorporates models that account for both the moon's gravitational influence and its motion through space, allowing lunar events and timing to be accurately synchronized with Earth-based clocks. The developers report that the system maintains high precision within tens of nanoseconds over a span of 1,000 years. So this software packages these complex calculations into a ready-to-use tool, simplifying the conversion between lunar and Earth time without the need for bespoke corrections. Its emergence reflects the growing practical needs of future lunar infrastructure, where precise timing will be essential for safe landings, coordinated missions, and general things happening on the moon. So I'm glad that they've thought of this, because it could be a problem in the future. So there we are, a good software product from Purple Mountain Observatory in Nanjing. And we now move on to talk about something else to do with the moon. Now, this is to do with ice on the moon. And believe it or not, this comes out of China as well. Now, the Chinese are sending the Chang'e 7 lunar mission to the moon this year. And they hope to find the elusive water ice at the south pole of the moon. And there's a problem. They've identified a problem with collecting the ice if they actually find it. And the problem is that exists under conditions of extreme cold and near vacuum. And at these temperatures and those pressures or lack of pressure, water ice is highly sensitive to disturbance. So if you put a drill or a scoop or anything into that ice, what's going to happen? Well, they are going to be warmer than the ice.
Yeah.
They slightly raise the temperature of that ice, meaning that the water will sublimate directly from solid to gas and disappear. And they're worried that even a small amount of heat may be enough to cause the ice to sublimate, and the water molecules will just escape into space before they can be collected. So it's complicated because they will have to make sure that any tools they use to look for ice or collect ice are going to need to be cooled right down.
Mhm.
But also, actually, if you think of, if you've got a scoop digging into the lunar surface to collect this ice, you've got to get it into a container really quickly before its temperature rises and it sublimates and disappears. So they're going to have to come up with some collection system that is very clever, cooled right down to at or below the temperature of the ice in the lunar soil, and they've got to be able to collect it, more or less instantaneously. So they're just pointing out that collecting ice on the moon is not going to be probably as straightforward as you would think. So there you are. Anyway, we wish Chang'e 7 the best of luck. We will be covering the launch of that when it happens. I'm not quite sure. Michael, could you look up when Chang'e 7 is launching this year? Michael? Is he there? No? Okay. So there we are. So that's the news for today. And we hope you enjoyed that. We will, of course, be back with more news next week. So...
yes, I will, Andy. For some reason, I was backstage.
Oh, okay.
All right, I'll be back in a sec.
Okay.
Rummaging around, were you?
That wouldn't be far from the truth.
No, obviously not. So there we are. So that's the news. Really looking forward to the launch of Artemis 2. So there we are. All right, then. Well, let's move on now. As we said earlier, the main topic for this week is Pluto, to coincide with last week's 20th anniversary of the launch of New Horizons to Pluto. Obviously, on January the 19th, 2006 is when it launched. And we thought the head of Dr. Alan Stern visiting us next week would tell you a little bit about some of the interesting science aspects of Pluto. Dave, are you there?
I am.
Okay, because we can't see you.
Oh, really?
So
Okay.
yes,
I can see me.
yeah. Would you like to expose yourself to? No, sorry, I'll rephrase that. Would you like to show the viewers that you're there?
All right. Well, I'll tell you what. I'll turn my camera off and on again. No, I mean I'm seeing all you guys with me.
We just got a black thumbnail from you.
That's very strange.
I'll tell you what. Do you want to go out and come back in again?
I'll try that. Okay.
Yeah. I was going to put you on before Lou, but Lou, do you want to kick us off with Pluto instead?
Yeah, let's do the interesting presentation first. And then,
Okay. Right. So yeah. So no, Dave's still blank, but never mind.
No. Okay. Can you hear me?
Yeah, we can hear you perfectly, Dave. But your video seems to have gone
Wow.
wrong.
So you can
Not
still
quite,
heckle,
not quite.
you can still heckle me even though we can't see you. So it's okay.
Yeah, absolutely.
Okay. Good. That's
Yeah.
the important part, right?
Anyway,
Before I begin, I want to make note that a good handful of my have joined the Space Oddities show tonight.
oh, hello,
So
Lucy. Welcome. Thank you for joining us.
so Connor and Shane. Hope I'm getting this right. I still don't know their name. Owens, and leading out. Oh, someone. Sophia. Sophia. So
Well,
welcome. And
you're
of course,
all welcome.
I bribed you to be here. So.
Oh, of course. And if you have any questions about Lou's presentation, make sure they're difficult ones and put them.
Absolutely. Absolutely. Your grade will reflect that. So my presentation, so I'm going to talk about Pluto's atmosphere later. Dave is going to talk about Pluto's surface. And so I've entitled this, Pluto, what do you mean it's not a planet? We're going to observe Pluto, a little bit about the exchange of atmosphere between Pluto and its largest moon. So I say Charon. Do you say Charon or Charon?
I say Sharon.
Sharon. Okay, Sharon. So let's get. Can I? Oh, here we go. It's working. It's thinking. Okay. So Pluto has an atmosphere. Who knew? The first direct observation that Pluto had an atmosphere was from the predecessor to Sophia, a flying infrared telescope. And it produced this light curve for Pluto's stellar occultation of the star P8 Mink Camola 1985. So remember that. Okay, that actually that 1980, the occultation occurred on June 9th, 1988, and it's plotted here along with, you can see its signal to noise ratio. And what you notice from this curve is that it dips down and back up, but it comes down at a bit of an angle. This will be important later as well. And that is indicative of a planet with an atmosphere as you cut through, as the planet moves in front of the star, off the star's light, but the atmosphere cuts off progressively more and more light until it becomes opaque and you're on the, this is an indication that Pluto had an atmosphere. Here's the same kind of study, only here we see an experiment replicated with the ALICE instrument aboard the New Horizons spacecraft. So the New Horizons, how the ALICE instrument count rate changed over time during the...
Sorry, Lou, your slide hasn't moved.
I'm what now?
Your slide hasn't moved.
Oh, I'm sorry.
That's it.
Ah, there we go.
There we go.
There. Okay. Lag here. You guys see it before I do because I'm so far away. Let me start again.
Newbie.
Here we see the same type of experiment, only replicated with the ALICE instrument on the New Horizons spacecraft. ALICE instrument count rate changed over time during sunset and sunrise observations. So in other words, New Horizons is behind Pluto, looking back at the sun, which at this point is pretty much a bright star because it's so far away. And so as Pluto moved in front, or actually the spacecraft is in front of Pluto, we can see the attenuation due to Pluto's atmosphere. The count rate here is largest when the line of sight to the sun is outside of the atmosphere at the start and end times. And so seeing is molecular nitrogen starting to absorb sunlight in the upper reaches of Pluto's atmosphere, decreasing as the spacecraft approaches the planet's shadow. As this occultation progressed, atmospheric methane and hydrocarbons, such as acetylene, for example, can also absorb the sunlight and further decrease the count rate. When the spacecraft is totally in Pluto's shadow, of course, the count rate goes to zero, or zero within the limits of the noise of the instrument. And as the spacecraft emerges from Pluto's shadow, you see the opposite occurring. So, more evidence that Pluto has an atmosphere. Pluto's atmosphere is rather remarkable for such distant icy world. Remember, the ability of a planet to hold on to its atmosphere is a function of, well, three things. One is the molecular weight of the molecule, or the weight of the atom that is in the atmosphere. So the heavier ones tend to stay, the lighter ones tend. The other is temperature. Well, Pluto wins out there because the temperature is very cold, not a lot of interaction going on with the molecules. But the third one that Pluto fails miserably on is the planet's mass. And so it should have an atmosphere that's accreting into space rather regularly, primarily of nitrogen with traces of methane and carbon monoxide. This exists in an environment where the temperature plunges to minus 238 degrees centigrade, or roughly 35 degrees Kelvin. I mean, super cold. Despite, though, the atmosphere is surprisingly warm and extended, stretches up to 3 times thicker than scientists initially predicted from stellar occultations from the ground. And this tenuous envelope is constantly replenished through the sublimation. We were talking about sublimation earlier today with the moon. Sublimation of surface ices, which creates a kind of delicate equilibrium between Pluto's frozen surface and its gaseous shroud, and Dave will be talking a little bit more about that. So here we go. This is just a graphical representation of the major component, mostly nitrogen with some methane and CO. There are other hydrocarbons in the atmosphere too, much lower mole, what we can say are mole fractions or contribution levels. Okay, from a paper published in November of 2017, Zhang, Strobel, and Imanaka, entitled "Haze Heats Pluto's Atmosphere Yet Explains Its Cold Temperature." Go figure that. So here we see this is a plot with temperatures, okay, and some of them are direct one. The black curve, that is the observation from New Horizons. So the challenge is put your physical models together and which one more accurately follows the black curve of the actual observations. It's basically atmospheric temperature and gas density profile of Pluto. So here we see dashed lines that represent the densities of nitrogen, molecular nitrogen N2, and methane in number of molecules per cubic centimeter. Is not shown, but it's well mixed in the atmosphere with volume mixing ratios like 10 to the minus fourth, so not that much. The solid black line, as we mentioned, shows the actual temperature profile derived by New Horizons spacecraft. Profiles calculated using the New Horizons pre-encounter model, see, and the latest gas-only model, yellow line, are also shown, but they're not great fits, right? You have to agree with that. The latter included in cyanide, HCN, so not only hydrocarbons but nitriles, and acetylene, C2H2 acetylene, but not water. Temperature modeled here, which includes these mediated heating and cooling. So this is a derivative of the haze impact on Pluto's atmosphere, which, by the way, is very similar to the haze and its impact on Titan. We won't be really talking about, but it is. So the Pluto-Charon system it's really more of a binary dwarf planet system. Charon half Pluto's size, and because its composition and density are about the cube that number, 2 cubed is 8, so it's got about 1/8 of Pluto's mass. But it is the largest moon relative to its body in our solar system, followed by our moon. Our Earth moon system. So they're mutually tidally locked, face to each other, right? Orbiting their common center of mass, or we also call that the barycenter, outside Pluto itself. All moons orbit common center of mass of their planet, but in Pluto's case, in the Pluto system's case, the center of mass is actually outside of Pluto itself, so they effectively orbit each other. This unique relationship makes them appear to orbit an empty point in space, and their 6.4-day orbital period means that Pluto always points the same face toward Charon, creating a complex gravitationally bound pair with significant surface features like Charon's massive canyon system, and I'm sure Dave will talk about that when he talks about Pluto's surface. I'll just say very little bit. Charon's surface consists primarily of water ice, intrinsic atmosphere detected. I'm going to point that out in a minute. And it makes it rather fundamentally different from its companion in that sense. But as we shall see, this is not the whole story. Aha, it's like a detective story. It's waiting. There we go. No, not the slide I want, is it? It's not the slide I want. What do I want?
I think you flipped over one.
Flipped over one. Okay, there we go. There. Okay, so you've seen this before. You saw this with the ground-based as well as the ALICE instrument on New Horizons, which went behind Pluto and looked at the attenuation of the sun's light as it went by Pluto. Here we're doing the same for Charon. So we see a similar solar occultation as observed by New Horizons ALICE, the ultraviolet image, but this time of Charon. So notice how much more quickly the light curve drops off and recovers, as opposed to the Pluto rotation we saw earlier. This is evidence of no or perhaps extremely tenuous atmosphere on Charon. So not really much to attenuate. Okay, so here's where I was hoping to go. By the way, this is these two images of Pluto and Charon are real images, but they're kind of blobbed together by some artists who put in smoke in the. You know, how much did you pay for the show? Okay, you get what you pay for. No belly ache.
Cheap is half the price.
That's right. That's right. Just lost my mind for a moment. Okay, got it.
No change there.
Atmosphere, as we said, consists mainly of nitrogen with traces of methane, carbon monoxide, and other hydrocarbons and nitriles. And some heating the sun, these gases escape into space, creating an extended exosphere that encompasses Charon's orbit. So about 0.2% of the flux escaping from Pluto's exosphere actually impinges on Charon's, provides a consistent and constant source of material for a somewhat tenuous and transient atmosphere on Charon, if you can even call it an atmosphere, which is cool. Under normal solar conditions, Pluto transfers nitrogen to Charon at a rate of about 5.7 times 10 to the 25th molecules per second. Okay, and this is sublimation of nitrogen ices on the surface of Pluto, escaping and then landing on the surface of Charon. Escaping methane from Pluto is captured by trapped in its cold polar regions. Over time, solar ultraviolet light transforms this methane into reddish organic polymers called tholins, which gives Charon its distinctive red North Pole, which you can easily see here. Nitrogen captured from Pluto can condense as frost where temperatures are extremely low. Simulations suggest that over tens of years, roughly 1 micron of nitrogen ice can accumulate in these cold traps. While nitrogen dominates the atmospheric exchange, methane oxide also escaped Pluto's gravitational pull, contributing to Charon's evolving surface chemistry. These tholins formed on Charon's surface through photochemical reactions may serve, here's the kicker, may serve as precursors to amino acids, suggesting the presence at the solar system's frigid frontier. So noodle on that for a while, Space Oddities. I will end there because I know we have a lot more to learn from Dave. So I'll
Okay,
stop there.
thank you, Lou. That red polar cap on Sharon is just amazing. And if you look at the close-ups of Sharon, it's such a distinctive feature. And to work out that it was, due to the transfer of material between Pluto and Sharon, makes you wonder, if there are any other examples of this sort of thing happening in the solar system. Maybe in the Kuiper belts you have, excuse me, binary systems where this sort of transfer occurs as well. So it's an amazing solar system, and the big lesson to come out of Pluto was firstly that nobody expected Pluto to be such an interesting dynamic world. I don't think, and said this before, that even at the frigid edge of the solar system, you still have activity and dynamic processes and changing landscapes, and it's an amazing system. And I'm sure we'll learn more from Alan next week. So there we are.
We do have some evidence of planet-moon exchange in the opposite direction.
Yeah.
Right from Einstein, where it's volcanic material spirals into the atmosphere of Jupiter, giving it its aurora.
Yeah, absolutely. Okay, thank you very much, Lou. That's absolutely great. So before we get on to Dave, a quick. This video is sponsored by Picastro. It's like Instagram for space nerds. For sponsoring Space Oddities, much appreciated, Tom. Just before we go over to Dave, in fact, I just want to give you a quick look at the timeline of New Horizons. We've talked about it. We know that it launched on 19th of January 2006, but what actually happened after that, because it took a long time to get to Pluto. So here's the timeline of New Horizons. As we said, launched on January the 19th, 2006. It was the fastest spacecraft ever to leave Earth orbit. Can't remember the exact speed, but it was a lot faster than anything we've sent out of Earth orbit before. In February 2007, it made a Jupiter flyby. The images from that were amazing, and there was lots of good science to come out of that Jupiter flyby as well. And then they put New Horizons, which is about the size of a grand piano, into hibernation to conserve power, and it was in hibernation for 7 years. And obviously they were checking it regularly. Every year they did a full system checkout, and then they woke it up on the 6th of December 2014. But then 10 days off closest approach to Pluto, they completely lost contact with the spacecraft. And to think that it had been flying all those years without any problems, and then 10 days before closest approach, they completely lost touch with New Horizons, couldn't get it to respond at all. Obviously, a really worrying, intense time for the New Horizons team. But, as they frequently do at NASA and JPL, they pulled it back from the brink, and finally, after 81 minutes of silence from New Horizons, they managed to communicate with it and get it up and running again. And the error was later traced to, believe it or not, a computer problem, where what had happened was that, if I remember correctly, they were sending commands to New Horizons at the same time as it was trying to write to its storage, and it couldn't handle both at the same time. And that caused the communication breakdown. But luckily, they managed to regain contact with New Horizons. And you can imagine, there's a documentary about it on YouTube somewhere. And obviously, extremely fraught, intense time for the team. Anyway, on the 14th of July 2015, it made its flyby of Pluto. It took 15 months to transmit all of that data back, because it has a very low bandwidth transmitter, which they put on the spacecraft to conserve power, and very low power, low bandwidth transmitter. So it did take 15 months to get all the data back from Pluto, but they got it all back. And then after that, it headed out into the Kuiper Belt. You may remember in 2019, at the beginning of 2019, it made its flyby of the Ultima Thule object, as it was then called, but because that had certain connotations with a certain fascist regime in the 1940s, whose name I will not speak here, it was renamed Arakoth. And it was our first close look at a Kuiper Belt object, which turned out to be what's called a binary contact object, where two objects came together very, very slowly, and stuck together. And that was Arakoth. Now, they were hoping that they were lucky that Arakoth was along Pluto's trajectory into the Kuiper Belt. It was just luck, and they've been searching ever since to see if they could spot a Kuiper Belt object that would similarly be on New Horizons' trajectory, so that they could do another flyby of a Kuiper Belt object. But unfortunately, they've never found one that New Horizons will be able to visit. And it's now heading through the Kuiper Belt, coming to the edge of the Kuiper Belt, and then heading out of the solar system. So there you are. So that's the timeline of New Horizons, and it was a long wait for New Horizons to get there, but as we now know, it was worth the wait because it delivered spectacular images and spectacular science. And Dave's going to tell us now, I believe, a bit more about that.
Okay, yeah. So let me share my screen. And
If you have any questions, viewers, don't forget to put them in the chat.
Yeah, please, and yeah, put them in the chat. And if the rest of you can just sort of watch the chat and then yell out a question, since it's hard for me to do now. Are you seeing my?
Give Dave my hard question.
I don't want your hard questions, Lou. All right. So, well, first off, I will. Well, let's see now. It's not up yet.
It's okay. Just give it a second. There you go.
Okay. There's
There it is. Yeah.
Okay. So first off, Lou mentioned a bunch of times I was going to be telling you all about the surfaces of Pluto and Charon, and that is not true.
What?
I'm sorry, Lou. I made a liar out of you. I decided I would leave. Well, I decided I would mostly leave that to Alan Stern.
After all our conversations over the cratering rates on Pluto.
Well, that goes into the heat budgets, and that's what I'm going to talk about here. Is sort of planetary thermodynamics. So this is planetary heat budgets in Pluto, or basically why is Pluto so weird, and why is it so unexpected, and what we found. So first, I'm going to start with this very simple geometry lesson. Okay, so the volume of a sphere, 4/3 pi r cubed. The surface area of a sphere is 4 pi r squared. So you notice right away that the volume of a sphere grows much faster than the surface area proportional to the increase in radius. In other words, a much larger object will have a lot more volume compared to surface area. And the reason that's really important, well, first of all, a really good example, and actually you mentioned this a little earlier, Charon. Turns out if you take a sphere that's 1,000 kilometers, let's say, in diameter, and you break it up into 8 equal smaller spheres, they will each be 500 kilometers in diameter. And so it turns out that 8 spheres of the same volume of material have twice the surface area overall as the original sphere. So basically, you can see that with the same volume of material, you can get a lot more surface area by having a smaller object. And the reason that's really important is because planets basically generate their heat based on the volume, and I'm going to go into that in a minute, but they lose their heat based on the surface area. So I'm getting to this in a minute. There are basically, well, there's 3 heat sources for planets, and there's 4 heat sources if you want to include satellites. Then the heat sources for planets are, first, the initial formation of the planet. There's just stuff crashing in. Now, this artist concept is maybe similar in some ways to Lou's picture with the clouds in it. It's a little insane. A planet, when it's accreting, it doesn't look like that. It gets hit by something large, maybe not very often. In fact, one of my mentors, George Wetherill, said, you could be living on the Earth when it was accreting, and the odds are in your lifetime you would not see a large impact. So that kind of thing. It's actually relative. I mean, it's relatively slow, I guess. Although geologically, we're talking about every few, giant impacts. It's gonna heat the thing up. The thing is going to turn into a ball of really hot matter. Now, a larger planet gets obviously more impacts because it has higher gravity. It's attracting a lot more objects, and the objects come in at higher speeds in general. So a larger planet now, a larger mass, and I'm equating mass to volume. And because I'm really right now only talking about terrestrial planets, because gas giants, the formation is very different for them anyway. But I'm only really considering terrestrial planets now. Mass and volume are fairly closely related. I mean, you could say, okay, silicates are much denser than ice. But actually, that makes the problem of Pluto worse, and I can get into that too. All right, so initial formation obviously goes with mass, with volume. After and during initial formation, there is a period of compression, different and often core formation, where basically like anything, as the gravity grows, as the planet or the object grows, it starts to compress. The heavier stuff tends to flow downward, tends to move towards the center, especially if it's something like iron or nickel, where it can even melt under the hot conditions of the initial formation, and can flow down towards the center of the planet. All of this releases potential energy and converts potential energy into heat. And so there's another mechanism for heating a planet. Again, this really goes along with the mass and the volume of the planet. The heavier the planet, the higher the mass, the more energy you will get out of this mechanism. And finally, radiogenic heating, basically the initial matter in the solar system before the planets formed had potassium, thorium, uranium, radiogenic elements that it got incorporated into the interiors of the planets, and then they've been since their formation have been producing heat in the interior of the planet, and of course the amount of this material inside the planet is again proportional to the mass, the size of the body. So you can see that a larger planet is just going to have a larger amount of interior radiogenic heating. So those are the 3 things. I will go really quickly into one that we're not really considering here, but tidal heating of planetary satellites, especially the satellites, obviously of the larger planets, is important, and it's the thing that keeps Europa having an interior ocean. It keeps Io blasting out volcanoes all the time, that sort of thing. The tidal heating, it's all a very different mechanism for heating, but it's only for satellites of large planets, and it's not really. I'll mention it, but it's not really relevant to Pluto. So, okay. So meanwhile, heat loss. It all takes place through the surface of the planet. Obviously, all the heat that's lost from a planet has to go to space, and the only way it gets into space is to go through the planet's surface. It's basically goes in 3 different forms. At the very end, it's always radiation into space. but before that, it has three forms, and one is conduction through the surface. Okay, it's the least efficient method, but it's basically a planet sitting there. It's very it's hot, and the heat is just conducting its way up to the surface and then being lost to space. Volcanism and resurfacing. You're making a slightly more efficient method where you're actually bringing hot material right up to the surface. So rather than waiting to conduct through a shell of solid material, you're bringing hot material right up to the top of the surface, and then exposing it to, obviously, again, so it can radiate its heat into space, and you can get a lot more heat out of an interior that way. But it's, when you think of volcanism, we're thinking of individual volcanoes, so it's sort of a spot kind of heat loss. It's not it's not global, although maybe it can be, and I'll mention that in a moment. And then there's plate tectonics, right? And that's what we have on Earth, and that is really the most efficient method of long-term method, at least, of losing heat for a planet. And you've just actually bringing up giant plates of material globally right up to the surface. So you're bringing material from the interior up in a giant conveyor belt, and it just brings it up, it cools off, it goes back down inside, and more comes up. So it's just a giant convection engine, basically, to lose heat. And so these and these are all the ways that things lose heat. And the way you look at this, it's all the heat sources are proportional to the volume, and the heat loss is proportional to the surface area. The accepted wisdom has always been that the smaller planets with a larger surface area to volume ratios would lose heat faster than larger planets. And so that after 4.5 billion years, anything small would have lost all its heat and basically would be just sort of conducting through its surface. And this seems to be borne out by observation. So we would look at a blank page. Okay. Oh, this is okay. Hold on a second. This was where I had a problem. So hold on for one moment here. What I needed to do, for some reason, it wouldn't let me put everything onto one set of slides, and I don't know why. But I just made up a second one. So, okay, bear with me for one moment. I will share my screen, and I'll put that in full screen. Okay. All right. So anyway, when we look now at, okay, there we go. Smaller bodies in the solar system, Ceres, the moon, Mercury, right? And you see these, 473 kilometers, 1,740 kilometers. Basically, when you see a surface like this that's covered with a lot of craters, and there's not much other activity, you know you're looking at an old surface. It just has not been able to resurface the craters. It hasn't done anything. It's basically geologically more or less dead, and that's an indication that there's just conduction going on. In other words, there's not volcanism, there's not plate tectonics. It's just kind of sitting there getting pummeled, and it's just conducting through its heat. So the smaller planets are obviously showing signs that, well, they're dead. They're just not, they're just not producing that much heat. Look at Mars, slightly larger. We see lots of signs of ancient volcanism, right? Olympus Mons, the Tharsis Bulge, various, volcanic lava flows and things all over the surface. Signs of canyons and things which indicate, surface activity, but currently nothing. So it did have heat. It did have to use these highly or more efficient mechanism to lose the heat, and it did it. And now the heat is pretty much gone. Okay, and then Venus looks like there's been widespread volcanic resurfacing all over the planet. It looks like there also may be volcanism still ongoing. Now, Venus is only slightly smaller than the Earth, so this maybe isn't surprising either. It still has retained some of its heat enough to actually keep volcanism going, and maybe even as recently as 1 billion or 500 million years ago, which is geologically recent, at least solar system recent. It may have been dumping huge amounts of lava out, onto the plains and covering the surface and losing its heat that way. And then, of course, we come to the Earth. Global plate tectonics, active volcanism. I don't need to go into that. It's it's the biggest terrestrial body, and it still has this heat engine going. It still has a lot of heat. It's retained its heat. So all this was basically, it all made sense. And it's why we thought when we got to Pluto, we're going to see a big dead thing with lots of craters and not much activity going on it. And when New Horizons got there, I mentioned the radius of Pluto is only 1,190 kilometers. And we skip ahead to July 14th, or skip back to July 14th, 2015, as New Horizons arrives at Pluto, and we see this following image. So there we go. Look at that. There's craters. There's an old surface, everything, and that's all great. Except this is Charon, and the problem is, here's Pluto.
The perils of live broadcasting.
Yeah. Well, anyway, in any case, so here's Pluto, and it is active. I mean, very at least recent activity. It's pretty obvious. It's not heavily cratered. It's showing areas of complete smooth, haven't been resurfaced. I mean, even in the Kuiper belt, even way out there, there's a cratering rate, that can be estimated, and we would expect to see cratered surfaces all over Pluto. Some that small should not have been able to keep its heat for that long. It's got 3.5 kilometer water ice mountains. It's got these plains that have been covered over and very smooth, unmarked with craters. It really doesn't make any sense. Now, you can say it's ice, so it doesn't need as much heat to melt it and do that. And I will talk about that. But it really was a surprise to everybody. And I'm hoping Alan Stern can shed some more light on it, because there are some ideas about what happened, but none of them make that much sense. So we look at some of the possible explanations. There's other stuff in the interior, such as ammonia, other compounds that would lower the melting temperature so that not as much heat is required for internal activity. It doesn't seem likely that there's enough of that stuff to do that. And when we look at the surface and what they can tell from the surface is a lot of the stuff that is on the surface is actually made of water ice, and not with not the kind of concentrations of stuff such as ammonia. And maybe even Lou can talk about that, because you would expect to find some of this in the atmosphere, and I don't believe there's much evidence of this kind of stuff. So that's kind of like, that's a tough one. Radiogenic heating more than expected seems unlikely as well. There's no reason to expect that there would be more radiogenic elements out in the Kuiper belt or wherever Pluto formed. It's likely that Pluto has a silicate interior, a core of silicates of rocks, which would have more radiogenic elements than we'd expect ice in the outer solar system to have. But even if you say that they have the kind of radiogenic elements that we have in the inner solar system, which is where we expected most of them to be, the amount of heating is the amount of heating to melt 1% of water. It turns out to be, and I did a back of the envelope calculation, which basically means probably wrong, but it would take about 12 billion years to melt something like 1% of this. And you have to think that if there's a core, it's melting stuff down inside the planet, and it's got to get to the surface. So you really need a fairly large percentage of melting to get some of this material up to the surface. So that's another tough one. Somehow the interior structure is weird, and it's allowed the heat to be maintained for a long expected period of time. I have no idea what could do that. I guess this is an idea, but it doesn't really. It's hard to imagine. And somehow the one idea that and maybe Alan Stern's going to talk about it, I don't know, is that whatever interaction resulted in the Pluto-Charon binary system was something that was more recent than we think, and that actually was a fairly, energetic interaction between the bodies, and actually created heat, and that heat has still been retained in Pluto, or is recent enough that what we're seeing is something that came from that interaction. But we don't really see an equivalent thing on Charon, although it's smaller, so maybe. Anyway, these are like the only reasonable explanations, it seems like, and none of them make quite enough sense. So no one's really happy with any of these explanations. But maybe Alan Stern can say something. I think we need to ask him. There is one thing that I like to say is, and maybe we shouldn't have been so surprised, is we look at Triton, which is Neptune's largest moon, which is likely to have been also formed in the Kuiper Belt. It's only slightly larger than Pluto, basically the same size, and it was actually in the same vicinity and was formed in the same vicinity of the outer solar system. It doesn't show a heavily cratered surface either, and so possibly this is another body size of Pluto, and it's been resurfaced, and it's still got some sort of recent activity, or recent enough activity that it did manage to retain its heat. Maybe we just don't know what we're talking about with icy bodies, and we need a new hypothesis. So there you go. But here we go. So now you know what to ask Alan when he's here.
Yeah,
I believe that's it. Yes, that's it. So thanks. And any questions? I don't know if there were, but let me know if there are questions in the chat, please.
The discovery of active geysers on Triton by Voyager 2 was a huge surprise, wasn't it?
Right. Yes. I mean, the same thing. It's tiny. It's cold. Where is this heat coming from? Now, the one thing about Triton is at least it is orbiting a large, Neptune. I mean, I don't know what the tidal, I mean, it may be getting energy from the tidal stuff. But Charon is too small. Charon and Pluto orbiting each other. First off, because they're co-orbiting and they have the same, they're facing each other. And the orbits are not, some widely elliptical orbit. The tidal forces are really, really small. I mean, they're just small bodies. So
absolutely,
yeah.
So
a couple of
for that.
comments, if I might. That was fabulous, Dave. And
please, yeah, thanks, Lou.
Thank you, Dave.
Well studied and well done. I love that you went back to first principles for all of this. It was great. No, I do. That was the way I found it to teach. Well, first of all, the bulk density of Pluto is about 0.85 or so grams per cubic centimeter. So there's rock, but there's also a lot of water ice. The water, if it exists on the surface, and it seems like it must, would be frozen out like steel, and there's no chance of sublimation of water. But the nitrogen and methane sublimating off the surface escape pretty readily, which requires a resupply from the surface, therefore from under the surface.
Yeah.
Otherwise, methane is a very fragile volatile. It's just going to get destroyed by the ultraviolet light from the sun. And then any other, ethane, ethylene, acetylene, those kinds of things, they're all photochemistry from the sun. So Dave and I chatted a little bit about the surface before today, and it seems that like volcanism of some sort, but I don't think any has been observed by
not current volcanism, but there are what are thought to be old cryovolcanoes there.
Right. So one other thought, and that is we don't really know where Pluto formed. do we?
Right. That's true.
It's got
That's
a lot
true.
of ice.
You're right.
So it's outside the frost line. Like, oh, that's great. Is it possible that like Uranus and Neptune closer in, its density would not suggest that, but what I'm thinking is the closer in you form, the higher, especially during the heavy bombardment, the higher your cratering rates are going to be.
Yeah.
And I don't know what the cratering rate is out at 50 AU.
Right. I mean, it's much more. Yeah.
But
I mean, is it a safe assumption that it formed in the Kuiper Belt, bearing in mind that there are bodies of similar size in the Kuiper Belt, and it would be a bit unusual if it wasn't originally a Kuiper Belt object, because it is right on the edge of the Kuiper Belt, isn't it?
Yes,
is,
I think that would be the go-to. Yeah, I mean,
Yeah.
that would be the go-to
but it was
assumption.
pointed out it's like Triton, right? And its density is very similar, most of them, of the outer system. So I don't know.
Right.
Yeah.
No, it's really, it's a mystery. It's definitely yeah. And you added to that, Lou. Right. You're right with the sublimation and then resurfacing or reacquisition or whatever you want to call it of methane and stuff coming back, has to come back up to the surface to replace that. It has to be active, and it's really weird. It was just it was probably the biggest surprise, I think, when they saw Pluto. I said, wait, it's not supposed to be active. So what is this thing doing?
Wasn't that true throughout all of the Voyager missions? We kept expecting just the logic you're proposing: further from the sun, less heat, less convection, lower wind speeds, that stuff. No, it was completely opposite.
Well, supposedly,
huge wind speeds.
Supposedly they had Saturn's rings completely figured out, the dynamics, everything. They explained everything about it, and they got the first pictures back from Voyager, and they threw everything out. like the next day, they were working on new models because everything that they thought was so obviously not correct just from the images that Voyager took. So yeah, that's why we do this, I guess.
Yeah, it's amazing. Well, hopefully Alan Stern can throw some light on this next week, and in your absence, Dave, we will ask him these questions.
Oh no, I'll be here. I'll be there next week.
You'll be here. Oh, I thought. Oh, good, great. If you're going to be here.
No.
Because I'm sure. So I'm sure he would love an opportunity to answer questions like this. Well,
or not, because you've just pulled what Marshall McLuhan out from behind the soda machine. Well, everything you've said about Pluto is completely wrong.
Yeah. I think it'll be an interesting discussion next week. And viewers, we do hope you can join us for our chat with Alan Stern next week.
Absolutely. Yes.
Actually, talking of that, you may wonder why there was such a race to get New Horizons launched when it did. Well, it was because Pluto's moving away from the sun.
Mm-hmm.
And it was expected that if New Horizons launched much later than 2006, by the time it got to Pluto, the atmosphere would have frozen out, just leaving us a sort of a featureless ball of ice. And that was why there was such a rush to get the New Horizons mission accepted and built and launched when it did. But I gathered, I was reading some research that said that actually that may not happen to Pluto, or at least not as much as we thought. Now that we know a lot more about the atmosphere, that atmosphere may, because it's always been assumed the atmosphere would sort of collapse onto the surface.
Right.
With decreasing temperatures. But now, given the composition that we know about the atmosphere of Pluto, that may not happen, or may not happen to the extent that we used to believe it does. But anyway, hopefully Alan can shed some more light on all this. So there we are. Thank you so much for that, Dave. Thank you very much, Lou. And there were, do excuse me, viewers, I spent 4 days in Prague last week and came back with a stinking cold. So talking of heat, it was lovely in Prague during the day. It was the first day we got there, it was -8 during the day, and it never got above -4 while we were there. So we had cold 4 days in Prague, but it was absolutely wonderful. I took my daughter there for her 15th birthday present, and we had a fantastic time. Anyway, moving on. Well, we're going to go over now to more familiar territory, because guess whose turn it is to shine this evening? It's Roger, and Roger will do as our guide to the night sky and the viewers gallery. Now, we had a massive solar storm last week, as you know, and you've been kind enough to send in some images of the unbelievable aurorae that were visible. So we'll have a look at those in the gallery as well. So Roger, in time-honored fashion, take it away.
Okay, can you all hear me?
Yes, we can.
Yay, that's good. Okay, so we're coming through the end of the first month and into February. Wow, where did that month go?
Yeah, exactly.
So we're gradually working our way through the phases of the moon through to a full moon in the beginning of next month. Whoopie-doo. And this is what it was like this afternoon as it was rising up to the night sky.
Beautiful.
So, there we go. More pictures to follow later. But should a miracle appear and there's a clear bit of sky tint descend, the moon will be traversing through the Pleiades. So there's an opportunity to put something into the gallery for next week. This image that I've inserted into the display here was one that I took last year, so it just shows you what can be done, and that was just done with a DSLR camera. So just go careful and see if you can spot the moon going through the Pleiades. You have been warned. So we are now working our way through at 10 o'clock. We've got the dominating Orion constellation with the moon up above, and Jupiter over into Gemini still. So we've got pretty much the winter circlet there of Capella, Aldebaran, Sirius, Procyon, Castor Pollux, all the way through. So that's a little interesting asterism, should you so wish to have it. Uranus is down below the Pleiades, obviously with the glare of the moon glow. It will be a bit difficult to see, so not to worry. But unfortunately at 10 o'clock Saturn is getting quite low to the horizon, but it's still quite good as soon as it does get dark earlier on in the evening. Right, but I've got a picture here of sort of sunrise and sunset, giving you the locations of Mars, which precedes sunrise. We've got Venus and Mercury quite closely together after sunrise. And as you can see, they are quite they are becoming more apparent as the month goes on into February, where Venus will become a much more apparent evening star. So people look out for that when that does happen. Okay, so we've got the good old famous constellations of Gemini, Taurus, Orion, and dominating the night skies, which is what we all love to see.
Yep.
And we've got Aldebaran and all that all through in the Hyades and the Pleiades all together as interesting constant viewing of that for anyone to see. Obviously, we've got Jupiter still dominating up in Gemini, which is quite nice. So have a look at that. And it's
is that your picture, Roger?
What?
Did you take that picture of Jupiter?
Yeah, that's with the new C Star S70.
Oh yes, of course. Yeah.
On a cloudy night, right?
Yeah. Anyway, so have a look at Jupiter. It does get very, very high for the Northern Hemisphere, which is great for not needing your atmospheric dispersion corrector. So get out there and have a good old look. Although we have passed the opposition of Jupiter by almost a month now, because it's such a big thing to see in the night sky, it's not really that much noticeable at the moment, unlike something like Mars, which would disappear almost into nothing. In fact, it's about the same size as Uranus in the night sky. So it's a pretty tiny object, poor little Mars, but there we go.
Oh,
It'll come back.
yeah.
So obviously with the moon coming through the Pleiades, we've got all these stars to see how they gradually get obscured as the night goes through, should anyone be able to see it. And it's quite interesting to see how the motion of the of our moon traverses against could make an interesting pattern. So we've also got, as I said earlier, the evening star of Venus there starting to appear. So it will be visible just briefly, for it does set shortly after the sun. But there we go. So we've got the moon, which will appear at the beginning of February, quite near to Regulus. So could be an interesting opposition there. It will be a waxing crescent slightly, but there we go. So we've got, at the moment, we've got 5 planets up, although some will be rather difficult due to the closeness of the sun from its glare there. So we've got Jupiter, Saturn, Mars, Venus, and Mercury all up at the night sky, but not always visible due to the closeness of the sun. Now, I've got a little bit of information about comets coming up through this year. We do have a few, but unfortunately some of these will be more suited for the southern hemispheres, but I will make you aware of them. This one, which will be more best viewed in the southern hemisphere. So this one is Comet 2024 E1, Virchow, discovered on the 3rd of March 2024. It's just past its perihelion by a week, and it will be roughly 1 astronomical unit away. So quite an interesting thing there. I haven't seen.
What was that name again, Rod? Sorry.
Virchow.
Okay.
Virchow.
Lost in
Something like
translation.
Yeah, whatever. Well,
Sounds like you've been.
yeah, I know. So there's that one. So as you can see from this path of its trajectory going right through, it will sort of go through into Taurus, but that won't be April this year. So it's going to be rather difficult. I mean, at the moment, it's about 40 degrees south of the celestial equator, so it's a definite no for us at the moment. So we'll have to keep an eye out for that one. We've also got 24P Schmaus. Take that as you like. All these foreigners, I don't know. So it will have reached its perihelion in January, and after that it becomes it's a morning object between January and March, so it will be visible both to the north and southern hemispheres, and it travels between Virgo and Bootes and heads on towards Serpens. So one possible thing to keep out for us. And then we've also got Pan-STARRS 2025 R3. So that could be brightest comet of 2026 maybe, but we'll have a look see later in the spring. And it's currently roundabout in Andromeda.
And I noticed it said it was possibly going to achieve great comet status, which means 100% definitely it won't.
That's right.
Absolutely. There we are. If only we could get a picture like that generated by AI. So that's roughly where it is at the moment, although it's slightly dated for last week. So it would have moved more towards the bottom right-hand corner of the square of Andromeda there. So keep an eye out for that one as well. And not to be missed out, we've also got Schwarzmann-Washman, which is down below, between Virgo and Hydra. So quite a few things going on in the night sky. It's just like the buses, except we got about 6 at the same time. We've got a little list here of some various other comets, although some of them will be getting quite a faint magnitude, as we can see in here. But there are some interesting ones that could make an appearance that may surprise a few.
Mr. Panstars is doing well, isn't he?
Yes, he is. And here's the view of the sun as it is of today. It's got lots of little groups of sunspots at the moment, not too many prominences either, and seems to be a lack of coronal holes at the moment. So it's sort of void of any activity for producing any spectacular things like we had last week, unfortunately. But there we go. Maybe we could do with the rest. Okay, and on with our humongous gallery that we've managed to accumulate thanks to all our viewers. And the first one we've got here is one from Lou. And this was with his C-Star S50 of M81. Okay, and this is what
Oh, lovely, Lou.
Nice.
Nice.
Oh, lovely.
Very nice.
Real. So I
Very,
just
very.
put the sea star outside and went back in and had some tea.
Yeah.
Astrophotography
pretty
wonderful these days.
Yeah. Very good for under 2 hours. Very good.
Yeah, very good indeed.
Mm.
And one from Jerry, which is the Cone Christmas Nebula. And this is what he's managed to produce of that.
Oh, Jerry.
Whoa.
Wow.
That's beautiful.
Lots
wow.
of lots of dust structures there. Well caught.
Yeah, lovely.
Beautiful.
Very nice. Okay. And then on to we've got a collection from Sandra here. She's got 4 images in from her S30.
Nice one.
So there we go.
Nice.
Okay, here number 1. It's
Oh,
the Heart Nebula.
Oh, Sandra, that's beautiful.
Amazing color.
What a-
Yeah, look at that.
Yeah.
Wow.
Mhm.
Wow.
Okay. And then her second one of the Pleiades.
Mm-hmm.
Mm-hmm.
I don't think I want to get this.
That's right.
Beautiful.
You can't get all Pleiades in S50, I don't think, field of view, but you can in the S30.
Oh,
No,
interesting.
yeah. You have to
got a
do
lot
a
of different
mosaic.
star colors as well. Very good.
Yeah.
Lovely luminosity. Look at that. It's beautiful.
Mhm.
I could do with that
Okay.
for next week.
Yeah.
All right. And then we've got the horse
horse
head,
head.
and we've also
Yeah.
got the flame nebula there.
Oh, wow.
Great. That's nice.
That's
brilliant.
lovely color.
Mm.
Well done indeed.
And her final one, I'm trying to remember. There is something there, but it's a bit faint.
That's a killer asteroid, isn't it?
You.
Yeah, there's something
There's
there,
a
but
whiff of something to
couldn't
star,
put it-
isn't there?
Right.
Yes. Anyway, so that's what she's managed to accomplish with her S30.
Well done.
Right.
Thank
And
you,
then
Sandra.
we've got another picture of we've got a Pleiades theme going through here on a few contributors, and this one's from Lee, which he also did with his S50. Now this is 7 hours and of 20 seconds exposures.
Wow.
So he's got to be using the wedge, an equatorial mode for this.
Yeah.
If you do 20-second exposures.
So there we go.
Wow.
Wow. Look at that.
That.
And
Wow.
look at his signature. That's
Yeah. Yeah, it's even got his signature in the Pleiades. I'll have to have a look out for that.
Skywritten. He had a skywriter. Sandra just said the image that you can identify Betelgeuse or Betelgeuse or what.
Yeah.
Oh, right.
And Fred says the Pleiades star clusters on the back of Subaru cars. There you are.
Yeah, there is. Yeah.
All right.
Oh,
Okay.
there you are.
that's
Thank you, Fred.
Yes, the badge.
Right. Right. We got some pictures here from Kenneth. Now he's decided to try out a new mobile phone, which has got some Leica lenses on it.
I like it.
So he's got a
50
mil lens, a 23 mil lens. It's a 70 mil lens,
Nice.
and a 100 mil lens, I think, on there, or a 120. So interesting to see what
Yes.
you get. So he's got it set up on as a rig, and he has been taking some quite interesting pictures with it. So
nice.
watch this space for some amazing.
I like a Leica.
Yeah.
I know. He bought it because of the capabilities that the camera was doing. So he's managed to get some aurora from near his place, Bergen.
Oh, look at that!
Oh,
And as you can see, it's right over Orion there.
Oh,
Yeah.
yes. Lovely.
Right in the
Yes.
centre there.
wow.
That's lovely.
That's done with this
Beautiful.
phone camera.
Oh,
Jeez.
goodness me.
And there's another one with Orion
Yeah.
over to the right of centre
Yeah.
as well.
The colours.
Amazing.
I'm so.
Yeah.
I've never seen an aurora, and I want to.
Mm. So even shining through the clouds there.
Mm-hmm.
Yeah.
Yeah.
Wow.
I know, it's almost a daily occurrence when he even bothers to get out. Oh, it's Orion. No, it's more aurora tonight.
Yeah.
Mm.
Here's one from Lee down in Delabole, North Cornwall.
Oh
With
no,
his,
really? Cornwall?
Yep.
Wow.
Yes.
Oh,
Look at
what?
that.
Oh, jeez.
Oh,
There's that sign writer again in the picture.
Yeah.
wow.
That
That's
must be
basically.
near to the Pleiades there.
Sandra says
Yeah.
she missed the aurora again. Yeah, I mean it was allegedly even visible from here in Spain, but I was in Prague at the time, but it was just rain here, so no chance.
Yeah. So well done, Lee.
Beautiful.
Did well.
Lovely.
And this was a picture of the moon that I took a couple of nights ago. Okay. So I got this picture
Wow.
here,
Yeah.
and
Nice
there was a lunar V and a lunar X. So that's where
Yeah,
the
there's
lunar
two of
V
them.
is up there, just highlighted there at
Yeah.
And I can see the X.
sunrise.
There's the
At
X.
sunrise.
Excellent.
X is even more visible. Caught that one almost perfectly there.
Yeah.
Yeah.
Nice.
So I just caught it at the optimum time, really.
Nice.
Because when between the time that you get a moon rise and a moon set, it would have changed about 5% in its phase over that duration, depending on how long it is up in the sky. But it's quite interesting to just get the capture of those just as it's hitting the tops of the shadows there and creating the optical illusion of the lunar X and the lunar V.
Well done.
Okay.
Beautiful. Beautiful.
Mm.
Okay.
Right.
Well, there you are. Thank you very much, viewers, for sending in your images again. And if you would like to send us your images, then attach them to an email. One image per email, please. Otherwise, Roger gets upset. And send them into gallery@spaceoddities.space. gallery@spaceoddities.space. And of course, you get your own little gallery on the Space Oddities website as well. So do keep sending your images in. We do love looking at them as always, and we are very appreciative of the immense skill that all of you show in taking these wonderful images that only a few years ago would have been impossible for amateur astronomers to take with equipment unless they spent a fortune. So there we are. So that's the gallery. Thank you, Roger, for that. Now, this solar storm that happened last week, Daz is going to tell us all about it now, because it was not record breaking, but it was certainly an exceptional solar storm, was it not, Daz?
It certainly was, and you just said I'm going to tell you all about it. I thought 15 minutes. So
okay, all right. Well, tell us a little bit about it then.
I'll tell you, I'll do my own program about it. Right.
Okay.
Anyway, just
all
to show, just show this. There we go. Can everybody see that?
Yep.
That's it. Yeah. The motley. Right, as Roger said, this is a picture of the sun. Now, as I said, what I'm going to be talking about last week's forum, and I've just noticed on here, Kenneth talking about the aurora says, yes, he's got it again tonight. So thanks for that, Ken the Wound. Because like Sandra, I'm not too far from Sandra. I was completely both nights because it virtually ran for. I was literally clouded out. Although I did go out with the phone, and I did take images of that direction when they got a little bit thinner, and you could see some colour through it, but it wasn't worth printing. But I did the road. I think I said to you lads, in Shrewsbury, they had some breaks in the cloud, and they had absolutely amazing auroras that they were able to catch. Lees down in Delibold. How good the aurora was. I mean, it was absolutely fantastic. Anyway, I'm waffling. I've got to stop waffling. Right. Okay, then. So as I said, this is the sun. As Roger said, we've got plenty of sort of like active regions. There is a coronal hole around here somewhere, but it's not very big at all. We'll have a look at that a bit later on. And there is a coronal hole around the bottom here, but we can, of the way, the angle we're looking at it. Remember, this is a sphere. It's a ball, not a two-dimensional thing. And I've got the Earth there so you can see what's actually going on. And they've got most of the active regions marked, but there's some more coming around on the so we could be getting some more. And as Roger said, we're going through this phase at the moment. You're sort of like 2 weeks, almost 2 weeks of big coronal holes, followed by 2 weeks, so some quite very large active regions. It seems to be running in a sort of like a bit of a sequence and all that, but we'll talk a little while. Right, okay, then let me move on. So, oh, sorry, I've forgotten something. I knew I would. Let me just come over here. Right, now I should be able to advance that. Right, so hopefully the next slide. This is a synoptic drawing of the sun. Now they do 2 of these every day. One in sort of like early morning, one in the evening. So you know, it basically shows us what they've done at that time. You can see they've got the regions marked, the active regions marked, and this is where all the activities go. And now remember, I've talked about all this before, what these numbers mean and all that. If you want to go back and have a look at the past presentations I've done, then you know you'll find all the information there, what these means. And these are basically what sort of flares they could expect as a prediction thing. And when you see 1, that basically means 0. You're not got there should be an X, but when you see 1, that means there's going to be no chance at all, because we don't like zeros. Nobody likes zeros. You can see this hole here. You can see my cursor. I apologize if it's a bit jerky, because I have noticed that my feed on you a bit blurred and a bit jerky. But you can see this black hole here. That's all we've got on there at the moment. But we've just missed a massive black hole, which we'll have a look at in a sec. So this is what you can see. Every day they'll draw this. And as you can see, the actual magnetic face of the sun, this all, and the rest of it, and that's negative there, but the rest of it is all positive. So we seem to be, when we had lots of broken up areas which are positive, negative, and I'm talking about magnetism here. Yeah, and so that's what we've got at the moment. So let me just advance. Right, as we all know, we're in cycle 25. This isn't what we've got. All these plots of sunspots numbers over the months. Each spot is a month, so we get them at the beginning of every month. So this is January, is December, is the end of December. Now, as you can see, we actually peaked, and there's a bit of a debate: have we actually peaked, or are we going to have a double peak, which we can see? I'll show you in a second. So what we got, this is in August last year. Then it dropped quite dramatically, and it seems to follow in the prediction line. It's dropped very fast there. It's come back up, and it's bobbing along. We're back up where the prediction line is. Although this has changed, I've noticed they put a little bump in here now. So we may be looking at they're possible. I think they're hedged on a double peak. So that's just 25. Again, it started in 2019. This is what the prediction is going to be. Remember, it's supposed to, but that is an average. They can be as short as 8 or 9 years, up to sort of like about 14 years. And as you can see, if you look at this line below, you can see here you've got from 1800, 1900, 2000. That is all the cycles going back there, and you can I mean about double peaks. They look like little volcanoes. Quite often and all that. So we're not out of the woods yet. We could possibly peak again. You can also see the width of them shows you that the length does vary. How we stand at the moment. So 25 are on the way down. Now, if you remember, this is what we call Bartels music. It's basically, or KP people call it as well. This is a plot of 2025. This is when we had this was the year possibly in August, which is down. But if you look at August, to be quite honest, not a lot happened. All these dots are the KP for every day. That but when you see the black marks, that is when we had storming. So really, it was we had a few storms, sort of like a spell. August itself was very quiet. But since we've sort of like supposedly entered the decline, we seem to be getting more and more. I mean, these down here are sort of like what's almost daily, because he's actually up in the Arctic Circle, so he's getting more of it. So that's 2025, and if you look in December, and again, so if I move on to this year so far. And here we are. This is what we've had this year. Now, because we're in the declining number of sunspot numbers, it doesn't mean we will not have storms. In fact, sometimes it looks like we get more than we do actually at maximum. And if you look down here, then we had last week, see it virtually almost lasted 24 hours. It was a very intense storm. And it took us a surprise, and I'll just go. So I won't blather on. So I've got to stop blathering. So that's the storm we're going to be looking at, and it's record making. I think it will be classified when all the analysis is done as a Carrington of back. And look at our previous presentations. That will tell you all about the Carrington event, which is our benchmark of all storms. Move on. Now, this storm started really on the 8th when we had an X19 flare from active region 4341. This is an image of this flare at the time, and this is just a plot showing you it's gone up in thing. As I said, you've got A, B, C, M. That's an X. That's the classifications of flares. We only usually see M and X, with X being the extreme flares. And as you can see, it kicked off. Now, as I said, when this flare goes, creates hell of a lot of X-rays. Across it'll have some solar energetic particles in there, or let's call it radiation. And this will arrive at Earth within 7 minutes, because it's creating lots of X-rays. It's light, it will travel. Sorry, the end of this week. Okay. So this is what we're looking at, thing that kicked it off, but it wasn't just a flare. Now this is I've got this on. What I'm going to do is this is last week. This is the 18th. Now if we go first, I'll start out. This is where you go and it flares off. Now did you notice also how it came all up through here? This shadow is a coronal hole, and this will play quite an important part. Sorry for the black. It's actually Earth moving in front of the solar dynamic orbiter. So it'll go off, and if you watch this area around here, you'll see all this light up as well. You can also see filaments lighting up. What it was is the shockwave went towards the coronal hole, and it was at the coronal hole. This whole thing, you can see all these filaments lifting off around it, and this, I don't know whether this is what destabilized it, but it will go off second. There you go, and you can see all this stuff coming up. There's a darkening all around here, which means stuff as it's coming towards us. Here's a close up again. So here we go. It will go off any second, up lifting off already. And then of course with this, so it's been associated with not just one but several CMEs, and all this reconnection again is creating extra. Talking about coronal holes. Again, here's the region coronal hole. Look how big it is, and it stretches from the southern hemisphere up into the northern hemisphere, and basically this is also an indication coronal holes like this. We are entering the declining phase. Now, what happened once off? We even saw things firing off actually in the coronal hole, so there was more being created. And there's an Earth scale just to show you what went on. Did somebody try to act?
No, I don't think so.
No, okay, fine, that's fine. So here we go. Again, I don't want to see that again. So here we are. Now this was the prediction. Now I've put here. Now this is the UK prediction model, and if as you can see, it said wasn't going to hit until 20th. Now this hit us around here. It hit us on the about 6 o'clock in the evening UTC on the 19th. Here you can see this is Earth. This is the actual storm hitting us. But look at what's behind it. This, and if you come over on the density of the radiation, all the stuff that's come off, all the matter, and it's been cupped in this thing here. What caused basically us to have 24 hours, literally, storm.
Wow.
But as I said, this took 4 or 25 hours to actually hit us. This was moving very fast, very, very fast. Here's the velocity as well. I can hear somebody talking. Is there?
No, I can't hear anybody.
Oh, okay, then. Well, I'm hearing things. The voices.
Cross line there somewhere.
So this is, yeah. So what we hear is this is the wind speed, and as you can see, it's white, which means it's up round here. In a second, how fast the wind speed was, and a lot of this was from the coronal hole. This is sort of like the flare and the storm, the CME, but most of this wind came from the coronal hole. Anyway, it hits us within 3 hours, 24 hours, which is very, very fast. They usually take 3 or 4 days. The 1973, if I remember right, when the war was going on, and a storm that hit us so fast, it actually created an electromagnetic pulse in the atmosphere, and around the Vietnam, the war was still going on, and dozens of electronic mines, and they all detonated due to the pulse of this thing actually hitting so hard. So there we go.
There is a question now. From Derek. saying what's the difference in temperature in that large dark area and the surrounding area. I don't actually know the answer. Do you know the answer?
Well, I think I've actually got a diagram in a second.
Oh, okay.
The actual temperature is, I mean, because it's going to be, but that is, as we call them, the solar energetic fuels. And this is what we sucked into the Earth's atmosphere to give us the aurora and stuff like that. But there's a lot more. This is a coronagraph image of the actual thing going off. Now there was a halo, so we knew it was going to come towards us. And if you go back to the images, it was to the south of the equator and to the east. So we would expect it all to move away, and maybe we will just get a quick clip. But that when we will talk about that black corona hole, don't call it a black hole. I keep doing it. The coronal hole that played a very big portion, because from coronal holes we get very strong solar winds, and what happens is that will actually pull all that storm towards the western side, which means it was pulling it towards, and this is what hit us. So that was the coronagraph. You can see it there, and just put like about 6 hours before it was due to hit us. This, I'm sure, is what happened to its sensors, camera sensors. The energetic tools, the radiation literally snowed it all out. So you can see there, this is from what we call an instrument on there, and it actually gives you stop-start images of flares as they go up. Of course, and this lasted for a few hours actually, as all the stuff passed through and it happened at the time. So it's you an indication of what we were expecting. This was about 6 hours before it hit us. Now this is the HP 30 and KP index, but instead of the KP index giving you 30 minutes, this is 3 hours. This is giving you 30. And I always use this one because it means that when you see a KP bar last 3 hours, so you've missed all of that. So this one gives you a better chance. If you know that there's something on its way, go to the HP/60 index, and as soon as things start to kick off, you can then go out and get your equipment set up. Otherwise, I mean, these bars is 30 minutes. You're basically going to lose 6 of them if you just wait for an HP 31. So this is quite a little tool, and as you can see, it hit us around the 6 o'clock on the 19th, and it carried on into the 21st, and it ended just before 12 noon, just there, as you can see. But as I said, each one of these is 30 minutes. They're never different. The KP index is it will go higher than KP9. If you look at the KP indexes, they all topped off at 9, but this one will actually take you up even further. So you know it's actually gone beyond 9. This one literally hit the ears looking 10, as you can see. 26. That's time it hit 10. So we knew it was going on. Now you would think this is fantastic. We're going to get lovely aurora, and to begin with, we did. But here is your real-time solar wind. Well, it's not actually. This is back last week. And here is it actually hitting us. Okay, we're looking at this part here for now. We've got the initial hit, which is here. And this red line, which is BZ, now remember, the storm has got to have a southern component, and this is telling us whether the storm has a southern component within it. Remember solar slinky? I was going to get it out, but no, if I did, we'll be here all night. So this is where it hit, but if you noticed, after a short while, about an hour, it flipped, then it came south again. So in this time, we were getting lovely auroras down into the lower latitudes and all that. But then all of a sudden, it flipped north. But it's also is when the time when the biggest magnetism and what we got that's the temperature when you were talking about Derek. You can see the temperature varying and really hit us, really bang us hard. Now, if we had had a south-facing component, the BZ was south-facing, so it's below this line here, we've had some big problems because you've got all of this. It looks as though it's just right when everything's sort of like really high, really tacked out. I mean, look at the speed. Speed alone was 1,100 kilometers per second, which is huge. Only is at the bottom here, and that stayed with a coronal hole for 2 or 3 days, and it slowly died. And this is why we got all this aurora. We were lucky that this actually did possibly flip north. We would have had ground event problems. We would have had currents. We could have had problems with. I mean, already GPS, probably downlinks from satellites and things like that. So we would have had all that anyway. So unfortunately, still out in the orbits in us, but we need time to. They were probably put into a safe mode. I'd like to see how Starlink did with their satellites and what the downlink was like with that. But again, this is all analysed because it's one very big storm. Like I said, it's a hell of a magnetic component. I think this is the SEPs. No, here's the SEPs. This is density. So there, that as well. The speed was really, really fast, and the temperatures up. So we know that this was a massive. At the end of the day, it will be classified as a Carrington type. So that's what hit us. But because it flipped, again, I think that is due to the coronal hole. As I said, when that went off, everything was coming away from us. It was pulled, but also it twisted the electronic that was within the thing, which I'll move on to here. So here we are. This is what normally happens. Of course, we've got our magnetosphere protecting us. Here comes the storm. This is just a drawing, of course. And of course, what happens when the shock wave goes? This is all compressed. Magnetic field lines. They will snap. As they compress, they will snap, and then they will peel back like a banana skin down here. And when you get to the reconnection zone, this is where the radiation is pulled back in. Now remember, these magnetic lines do not all originate from the North and South Pole. They can pop out here, they can pop out there on both sides. So the more that peels back, the more it's going to come down. It's going to be lower. So that's why we get the lower auras. The more energetic set particles that are in there, the more that this is pushed back. But normally this will present hardly into the ground. But with this one, as I said, it did actually push it back. But because the north component disappeared. Now here's a typical CME. This is what I call the magnetic flux rope that's actually running through it. It stays connected to the sun, and all the way through here, that it's got electronic particles and plasma and everything, all that flowing through it. Now, if you go back, please watch all our other presentations, and then what we will see, what the magnetism is in here. Imagine a slinky, the solar slinky, as I call it. It's round. It's a tube. Now that means the particles on the outside of that loop are spinning around that and spinning up and down this rope. And basically, horizontal to us, it will give us a safe component. The front edge could be going north, but the back edge will be going do it the other way around. And through the center, you can see this center line, the darker purple line. That is what they call the axial magnetic and that will be your pointing either east or west. As long as you've got a northern component, south component, that will switch the auroras on. Now, that if it turns horizontally, like I said it did, and that turned off the aurora, that possibly means it twisted, and it gave, if you imagine you turn from horizontal to vertical, but if you clench your fist, put your thumb up in the air, and the thumb's pointing, if you look at and then take the wrap round, you're looking at, you've got a western, at the front, a western direction, at the back a direction, but you've got a north. That will switch the aurora off. If you turn it up the other way, then you get your southern again, because now your thumb's pointing south. That will switch the aurora on. And that's what seems to have happened, because the aurora did come back. So well, I'll keep on talking about the BZ. I'm going to just quickly flick through these. What I'm going to ask you to do is basically, this explains the components of a solar storm. I'm just going to put them on there, and if you want to look, please come back, just stop it, and then you can read what the different components mean. But the one we are, this is the BT component, but the one we are in is the BZ. This is the one that switches your auroras on and off. So the storm was a very big one. It took us by surprise. Took 24 hours to 25 hours to hit us. It did cause some lovely auroras, but because of it managed to twist it, and it looks like it switched the corona off to begin with, and then it came back. The last one, yeah, that's the last one. So here you go. I hope that that made a bit of sense. So
Right.
yeah, let me just get rid of that for you.
Very, very interesting. Very interesting. So, so anyway, let's see if we do get one towards the end of the week. So thank you, Andy, for that. And we will see. Keep your eye on the sun. And in the immortal words of George Harrison, here comes the sun. So let's move on. Dave.
Okay. Yeah. Let me get my screen up there.
Dave is going to give us another one of his wonderful look back at years anterior.
Can I just say hi to Andy? I think that's Andy who followed Tamitha Scoff, the space weather. If it is, nice. You probably see me occasionally on the Tamitha's show. So
Right. Okay. So Lou seems to have disappeared. Anyway.
Oh dear. Yep.
It's a particular
in disgust. He only had one.
Yeah. Dinner time for us. Okay, so I've got 3 weeks now due to various reasons. So I'll try to do this fast, because I see it's very late and people probably have other things to do in their lives. So maybe not. I don't know. Maybe not. Maybe that's why they're here. I don't know. Okay, January 11th, starting out. Uranus moons, Titanium and Oberon, are discovered by William Herschel. Who actually was also a composer, which I didn't know, and I guess that was interesting to see.
Yes, you ought to look up some of his pieces. They're really lovely.
Really? Okay, interesting. And that's
he was quite an accomplished performer of the in which he played in Bath and composed quite a lot of music.
Yeah, he did.
Okay. That's impressive. In any case, I did not know that, but he did discover Titanium and Oberon on January 11th, 1787. So I'm not going to do the math. That was a long time ago. But that's a little model of his telescope. That's not it, but it's a model that was made of the telescope that he used. So, okay, January 14th, 1970. OAO2 makes the first satellite observation of a comet. So the first time a comet was actually seen from space, it was in the ultraviolet, and it actually was an observation, not a picture. And that is not a picture from the OAO, by the way. That's just a picture of comet Tego Seto Kosaka. I hope I got that right. But it was the first observation. It was actually ultraviolet data from the comet. But it was, at the time it was launched, the largest uncrewed satellite. Of course, they'd had launched larger by 1970. Obviously, even some Apollo missions were larger satellites, larger things launched into space. But this was the largest one launched by NASA. And the other kind of important thing, or at least kind of cool thing, is that my father actually worked on the OAO-2.
Really?
With Grumman. Yes, he worked on the ultraviolet instrument and the wiring and stuff like that when he worked at Grumman Aerospace, who built the OAO instrument. So it's kind of cool. January 14, 2005. I guess this is another one that's going to make everyone feel old. I'm sorry about that. But
God, no, don't tell me.
Huygens probe. Yeah, I know. 21 years ago. I'm sorry, but me
too.
Me too. So I think everyone must remember this. I mean, this was unbelievable. First images from the surface of Titan, and it showed and actually showed basically eroded rocks on the surface, and obviously not water, but some sort of some hydrocarbons, methane, ethane. We don't know exactly what. But it looked like, basically, this looks like the same physical things as a dry lake bed on the Earth. Just unbelievable, I guess.
Because the surface was actually quite mushy, wasn't it?
I guess so. Yes, that's right. Yeah. Also, it was. But I guess sometimes the amazing thing about seeing pictures from other bodies is when you see. It's amazing how different the stuff is. But sometimes when you see stuff that looks like it could be Earth. To me, that's sometimes even more amazing. I don't know. Anyway, all right, let me go on. January 15th, Luna 21 landed on the moon. It deployed
Lunokhod. Oh, bless it.
Yeah, Lunokhod 2, second robotic lunar rover. They lasted 4 months. It covered 37 kilometers, and it was all controlled in real time. So there's a little control room down there at the lower left. That's an actual picture from the control room. And you see, he's got his hand. It's a little joystick. I mean, that's how they controlled it. Because of course, you have basically a 2.5 second, 1 1/4 second each way delay to the moon. Amazing. So you can do that. Unlike Mars, where you got to plan everything out and move the thing a little bit, see where it is, plan everything out for the next day. This they could do. They could just sort of drive along there. January 17th. Okay.
Sorry, Dave. Can you just
go ahead, please?
Put it back to Lunokhod for a moment.
All
I was going to say was this: Lunokhod proved quite conclusively that Russian space vehicles are made from vacuum cleaners and bits of old tractors.
Yeah, I know. It was a little tub with a little the cover up on the top there would open, and it had solar panels on the inside, and then the equipment was inside. And actually, I don't remember now if it was Lunokhod 1 or 2. I think it was 1. It was in a crater and it opened, and the thing brushed against the side of the crater, and when it closed, it dumped a bunch of dust inside. And then what happened was I guess the next time they opened it it overheated, and a lot of the component it failed.
What a shame.
Yeah, because the dust is so dark, it just sucked in the heat. So yeah. All right. Okay. So here's a more astronomy related one. Hubble published his iconic paper showing the universe expanding, and that was on January 17th, 1929. So
the year my mum was born.
Okay. Yeah. All right. Anyway, so that's I mean, again, this was one of the seminal moments, I think, really in astronomy history, science history, I would say. I mean, imagine the universe is expanding. Anyway, not much to add to that. It was an amazing thing. Comet, second comet discovered by 2P Encke, discovered by Pierre McCain. It was called Encke because it was actually Johann Encke who discovered that these different apparitions of the comet, which were observed, Messier including, observed that it was the same comet, and so he ended up getting it named after him. And it is a probable apparent body of the toward meteors. But for all of you out there, if you do discover a comet, make sure you get your name on it quickly, because otherwise some mathematician is going to come along and steal it from you, probably. Okay. January 24th, Voyager 2 becomes the first and only spacecraft to fly by Uranus. Yeah, 40 years, right. So,
God.
wow. Yeah, I know. That was Voyager. The Voyager mission was one of the things that kind of defined my career, because something happened. It passed by a planet at different stages in my, sort of scientific or academic career. And this was when I was in graduate school. I remember went by Uranus, and that was pretty cool. Launch of New Horizons mission to Pluto, January 19th. Well, there you go. So this is timely, and we've already mentioned this a bunch of times. The important thing to know about this was that the day this launched, of course, and even for a year or so before it, they knew that New Horizons was going to reach Pluto on exactly right on July 14th, 2015. And the important thing about that was that meant that I knew 10 years before my 57th birthday exactly what I was going to be doing on that day.
Oh.
So there you go. Well, either that or I was going to be sitting in a can with ashes in a closet while my kids tried to decide what to do with them or something. But anyway, okay. Anyway, yes. So that was kind of cool, actually, knowing all these years while New Horizons was heading towards Pluto that it was actually going to get there on my birthday, which was kind of neat, I thought. And now okay. So that's the end of those 2 weeks. So what I need to do is, okay, I'm sorry. Let me quickly get to the next presentation for the last week here. And I'm trying to get through this fast, but I'm not succeeding. All right. There we go. No, I'm trying to. Okay, I'm sorry. I'm trying to get out of this.
Don't worry.
I'm not succeeding. So little technical difficulties. All right. Let me go here. Okay, it seems to be doing something. Uh-oh. Okay, cool. All right. So beautiful screen. Sorry. Okay, I hope it's coming up. Okay, it's lagging a little bit. It should. There we go. Full screen. Okay. All right. So, okay, getting to January 25th through the 31st. Okay, so yes, first off, can't really go by without mentioning this. And I'm sure everyone remembers 1986, or most of the people here anyway remember that. And then January 27th, 1967 was the Apollo 1. And on January 28th, 1986 was the Challenger disaster. Not much to say about that. It was a horrible thing, and I know a lot of us just remember. Yeah. Okay. Okay. Back to our our theme, I guess, basically is actually this January 29th. So coming up in just a couple days, 1930. So that would be 95 years. Wow. Okay. Clyde Tombaugh finished his 6-night observing run. And that led to the discovery of Pluto. So he'd finished all his observations. He hadn't found Pluto yet. He found it a little later, looking through the images. But here are his original images. So from January 23rd, and then on January 29th, and the little dot was shown by the arrows is Pluto. And somehow he saw that and figured out it was a planet. So good for him. Unbelievable. Yes. All right. January 31st, of course, sort of the beginning of the U.S. space age, I guess, launch of Explorer 1, the first U.S. satellite. And January 31st, 66, Luna 9, first spacecraft to successfully soft land on the moon. And the first, and obviously that's just sort of an AI-generated picture there on the left. But the picture on the right is actually, the image is sent back. So the first images from the surface of the moon sent back by Luna 9, which was another amazing accomplishment, because 1966, think about that, that was less than 10 years after they'd actually just launched a little tiny beeping thing into space, and they were actually landing on the moon and taking pictures. And I believe that's it. Yes, it is. So, okay, thanks.
Thank you very much, Dave. That's great. Thank you so much. And
I mean,
of course,
you say
it was
that,
the year
Dave. Sorry.
I was going to say it was also the only year, of course, that England won the World Cup. So
Still celebrating.
so
No, I mean, you say that, Dave. I mean, basically, I mean, my lifetime and Andy's lifetime, we basically, the space race is our life, literally, right
yeah,
Oh,
from
me
the
too.
very
Yes.
when we
Yeah,
were
no.
born. Yeah, so it's yeah, all this has happened every time, and it's been a
well,
one
we were
line,
born. We were born.
and the journey continues.
Absolutely.
Go ahead, Andy. What were you going to say? You were
I was
born.
going to say we were born the year that NASA was founded. So we are true.
Right. Yeah. Me too.
True children of Apollo. We are.
Well, I
So,
joke that the space age began in October 1957.
yeah.
I was born in July 1958. So I joke that I was conceived at the birth of the space age.
Not because of it.
August, September, October. About 9 months.
All
Obviously,
right.
somebody thought the end of the world launched a satellite. Oh, well, what we're
Yeah.
going to do for the next 5 minutes? Okay, then. Let's make
Who
tea.
knows? You know. That's what I say. Right. My dad worked in the aerospace industry, so maybe this was so shocking he had to come home and.
Press release.
Okay.
Okay, I'm
Right.
sorry.
That's okay. Yeah, Fred said one of the leads, an old former physicist, when I was a poll worker 2 or 3 years ago, said he held things in his hand which are now on the moon. Wow. So fantastic.
yeah,
Thank you for
yes,
that,
yeah.
Fred. Thank you very much. Okay, so we're going to move on. It's time to don the hazmat suits and enter into the nuclear reactor that is Einstein of the week. And as you may know, viewers, every week for a bit of light entertainment, after all the heavy science, we have a look at what people have been saying on social media about the universe and related things. So let's just get Einstein of the week up on the screen, and we will have a look. I haven't got many for you this week, but I promise you there's one which is the Einstein of the week to beat all Einsteins of the week. So let's have a look. This is I think you'll enjoy this. So sorry, what?
What did Alan Stern say?
Alan Stern is on the program next week. So yeah, excuse me, got no idea what happened there. Let me just try that again, and we will try it again. Let's find out why that happened. That's really interesting. Okay. So anyway, Einstein of the week for this week. Let's hope that when I do this, it doesn't come back. Okay. Right. So meteorite angels. Now, why do we have meteorite craters on the Earth? Well, obviously because
meteorites,
they're the impact items.
Have hit the surface.
That's where you're wrong, because Ella Fleur said there are 200 craters on the Earth. 200 Watcher angels descended from up high. I believe this could have come from the Watcher angels that landed on Earth before they met on Mount Hermon to make their pact. What do you think? Well, Ella, if I told you what I thought, you'd be very angry with me. So according to Ella, meteor craters are formed from descending angels who are obviously not very good at flying. So
that's nice.
So
Yeah, they're a bit heavy.
Yeah.
And there's 200. Exactly 200 craters on
well,
Earth.
actually, I looked into it. They're actually 170, but there we are. So she wasn't far out, bless.
Okay.
But now you know, meteorite craters are formed by angels hitting the Earth and not lumps of
Watcher
rock.
angels.
Yeah, Watcher angels, not your common or garden angels. Watcher angels. Okay, next one. The ISS as a target. Somebody had an idea, a bit worried about Imagine China hit it with one of their space-based DEWs, that's directed energy weapons, or a UFO flew by it and made it explode somehow, such as when a SpaceX Falcon 9 exploded on the launch pad as an object appeared in the video moving at extreme speeds. It happened. No, it didn't. Somebody a bit worried about aliens making the ISS explode. Okay. Next one. What is Fahrenheit? What is Fahrenheit? Somebody tell me.
It's the temperature that we use in the U.S.
Yeah, you do.
The temperature scale the
It's a temperature scale. No, it isn't, I'm afraid. Dave, you got it all wrong.
Oh, man.
Nope. Fahrenheit means percentage hot. When it's 0 degrees, it's 0% hot. When it's 50 degrees, it's 50% hot. And when it's 100 degrees, it's 100% hot. So now you know. So there you are. Okay.
But that's I don't know. Yeah, I don't get that.
Okay, so it's a percentage.
Yeah, it's a percentage, but I think you'd have to qualify 100% hot. Yeah, percentage hot relative to what exactly? But there you are. So get your sunscreen out. Summer is coming. And lastly, this evening, this one is just unbelievable. Those of you who've got telescopes, you need to be careful because you're dealing with demonic optics. And why are you dealing with demonic optics? Because NASA has rigged all consumer telescopes with demonic optics that misidentify and distort whatever's being viewed. This also goes for binoculars, spotting scopes, microscopes, camera lenses, as well as all lenses that could be used to construct homemade viewing devices. If you ever look through such devices, you've given your soul to Satan.
Oh my.
Oh dear.
We're doomed. We're doomed.
Well, you know, yeah.
Demonic optics.
Well, now that it's out there, I have to tell you, my first couple of years at NASA, we're working on these demonic optics.
Yeah. Now,
so Hubble's one.
Secret's out.
I mean, I thought this had to be satire or something, but I looked into it and it's not. It's serious.
Oh boy.
Somebody does actually believe that NASA are putting demonic optics.
Just look at the title
telescope.
where it's. Yeah, just look at the.
Yeah,
Flat Earth official.
Yeah, I've no idea what the Space Monkey Challenge is, but I think somebody's just won it. Goodness me! I mean, this is just completely over the edge, isn't it? This is just.
Well, we should ask Lou if he worked on that stuff. I think since he's not here now. Since he's not here.
Yeah.
Got to get all our telescopes X into.
Yeah.
Yeah. It sounds like
it's a new way of calibrating. Get your telescope excised.
Yeah. So from now on, we're not going to ask viewers to send in their images to the gallery. We're going to ask them to send in their demonic pictures to the gallery.
Send in your devil pic.
Yeah, send in your Satanist pics. So there we are. And Kenneth says quite rightly, I feel sorry for people like that. Yeah, I think we all do, really. But some people are just completely over the edge, aren't they? So there we are. So anyway, that is Einstein of the Week for this week. Hang on, I've got a problem with my mouse now. Excuse me one moment while I try and resolve this. And so sorry about that foray into lunacy, and I hope there'll be more next week for your entertainment, delectation, and delight to viewers. And there we are. That's Einstein of the Week. Before I forget, thank you all for your contributions tonight. Big thank you to Stuart for replenishing our caffeine levels at buymeacoffee.com to such an incredible level. That will keep us going for at least another week, Stuart. So thank you very much. Thank you to Gerard as well, and all of those of you who've contributed to our coffers to keep Space Oddities going. And lastly, this evening, we are going to move over to Constellation of the Week, and the draw fell on Roger tonight to give us the Constellation of the Week. So just give me a second while I get this up on the screen. And Constellation of the Week, take it away, Roger. What have we got tonight?
Okay, so we're looking at Ursa Major. I don't think we've done it before. I haven't seen it on our. I'm assuming that we have not. So here we go. So the Great Bear of the Northern Skies. So we've all.
Neowise in that picture.
Oh, could have been.
Mm-hmm.
Yes, it is actually. Actually, this picture is one of mine, where I've highlighted the constellation Ursa Major and its proximity to Comet Neowise, which was 6 years ago now.
Oh no, really?
Oh, well, you again now, haven't you? Made us feel old. Because that
We're
must
just trying to really.
dusk.
Good,
Yeah, sorry, I was
good,
going to
it's
say
not
that
just
must be
me.
a dusk image. It was dusk and dawn.
Yeah,
Yes, through my demonic lenses.
yeah.
Well, now we can't trust anything anymore.
I'm surprised it hasn't got horns on it. Anyway, so everyone is obviously quite familiar with the with this constellation. We obviously call it the Plough or the Great Bear or a few other things that it is known as.
King Charles Wayne.
Oh right, okay.
Mm-hmm.
In Latin is called the Great She Bear, which is also paired with Ursa Minor. So contains 135 stars in its area there. So and it covers 1,280 square degrees and is the third largest northern hemisphere constellation. So there. That's probably why Michael hasn't touched it. So here's a general layout of the constellation. As you can see, the stars do spread out quite a way. I just sort of bring you up to the point here where we've got Lambda and Mu Ursa Major, which is Tania Borealis and Tania Australis. So that's quite an interesting naming of those two stars.
Yeah.
So we got the northern and southern, whether that means pole or something. And then we've got Alula Borealis and Alula Australis as well.
Wow.
So it's sort of the rear, right, and left feet of the constellation there. And of course, we're all familiar with most of us know the name of the major stars there as well. But we'll get on to that. So is Epsilon Ursa Majoris is the brightest star according to this at magnitude 1.76, 81 light years away, and is a type A star. Aliath also displays some variable brightness due to magnetic activity, classified as an alpha 2 Canum Vectorium type star. There. So there we go.
Exactly.
Merak is the Beta Ursa Majoris, which is in the Bear's Hip. That is 2.37 magnitude and a lot nearer at 79 light years away. And with Dupay, it points up towards the pole star. So there we go. It's 3 times the solar mass and radius, and the surface temperature is twice as hot as our sun. So is that 200%? So that's really, really hot then. Dubay, which is 1.79 magnitude, is an orange giant, and it's 124 light years away, and is not a member of the Ursa Major moving group, unlike the rest of the other stars that form up this constellation. And then we've also got, if you've got good eyesight, the double star Mizar and Alcor, So have a look at that. If anyone is able to spot that, you've got quite good eyesight. Don't need to go to Specsavers. And other stars in the system, we've got Megrez, which is delta 0.3.3, Thecta, which is gamma 2.44 magnitude, and Alkide, which is 1.85, which is a blue-white star, 101 light years away. So, what's its mythology and cultural stories? So, Greek myth, Callisto and Arcas. So, we've got Callisto, the huntress nymph beloved by Zeus, and jealous wrath, whose fury transforms Callisto into a bear. And then Zeus placed the mother and son Arcas among the stars, creating Ursa Major and Ursa Minor. So there's always some drama going on with the Greek myths of these constellations, isn't there? Okay, so that's as there should be something coming on. Where has it disappeared to? Right, so what other interesting objects do we have in Ursa Major? Well, we're mostly familiar with M81, Bode's Galaxy, M82, the Cigar Galaxy. We've got the Pinwheel M101, and we've also got Messier 97, the Owl Nebula. So we've got 4 Messier objects of interest here. And these are all my images that I've got of these 4 Messier objects, just to give you a comparison of what these objects are, should you not be familiar, although we have seen one earlier tonight of Messier 81 from Lou with his sea star. Of course, the smallest ones of the 4 objects here is the little Owl Nebula, which is quite a nice little object to capture if you are so interested. So we've got roughly 21 exoplanets in the constellation. We've got, as we've heard earlier as well, 135 stars in the constellation, covering 1,280 degrees of the sky. And that's what we can find for Ursa Major.
Thank you very much. That's fantastic. Thank you, Roger. You know, everybody knows it, but there's some really interesting things in there. So,
yes.
Okay. Let me just get rid of this, and there we are. Right. Well, that just about brings us to the end of this evening, viewers. Derek, we've run over time tonight by about half an hour. Sorry about that. Don't punish us too hard. But we hope you've enjoyed yourselves, viewers, and we will be back next week because next week we have Dr. Alan Stern, as I've said earlier, and we'll be chatting to him about Pluto. So if you have any questions about Pluto, anything you want to know, he is the man to ask. So get your questions about Pluto ready for next week. Before we close, Alan Stern is very much in favor of the fact that Pluto is still a planet and not, as it was, demoted to a dwarf planet. Let's do a quick straw poll among viewers. How many of you viewers think Pluto should be still a planet? Put yes in the chat if you think Pluto is a planet, and put no in the chat if you think it deserved its demotion to the status of dwarf planet. So let's just do this very quickly. Yes, Pluto should be a planet. No, Pluto should not be a planet. Put your yes and no's in the comments in the chat now. Andy Cowley says yes, Pluto should be a planet. Sandra thinks it should be a planet as well. Any more? Bob LeBlanc says no, it should be a dwarf planet.
Elena says no.
Elena Cipollini says no. Kenneth says great show again, thanks, and says yes. So it'll be interesting to talk to Alan about this. I'm sure he's sick of talking about it. But let's see if we can come up with some more interesting questions about Pluto that he doesn't normally get asked for next week. But there we are. Anybody else want to say yes or no before we close the poll? No. Okay. Nobody got any opinions then? Okay. Right. Well, thank you for that. And I think the majority seem to be in favor of Pluto remaining a planet and not being demoted as it was at the infamous now meeting of the International Astronomical Union, where it was decided by a vote after most of the people had left the conference that Pluto was going to be demoted. So Gerard says yes. So yeah, I think the yeses have it basically. So thank you, viewers, for being with us tonight. We have been Space Oddities. We will be back next week with Dr. Alan Stern, and the week after, well, we'll let you know about that when we finalise what we're going to do. So yeah. So thank you very much. Thank you all for your donations and coffees and everything. Much appreciated as ever. We will see you next week, where we hope you can join us for our chat with Dr. Alan Stern. And until then, have a fantastic week. May the weather remain good where you are, and clear skies, and take care of each other. Look after yourselves, and thanks for being here. And we'll see you next week. So from all of us at Space Oddities, we will bid you bye.
Thank you. Good night.